I take this age estimation network again, and I load it. I did it before. It's now reading it from the internet. And I have here my net chain. You see, everything is in Mathematica with these square brackets. By the way, if you see Mathematica, let's make a new notebook. If you want, let's say, the numerical value of a thing like pi, you can actually write a pi. And come on. And you can take the square root of pi. And Freddy's asking, if you ask for the numerical value, you get this. But if you ask, let's say, I want 100 digits, you get this. But if you ask for 1 million digits, you get 1 million digits. And it's a pretty long number. But Mathematica is quite precise. And if you do, for example, some algebra, you can do, let's expand some formulas, x plus y, and do it to the power of 2. And normally in Python, you write this. Well, this is from the 80s, 90s. This is a really long time ago. And people write SQRT for a square root. And this is so old-fashioned. But everybody does this, millions of people. It is more or less ridiculous. So what you do is you just type Control 2 and you get this. And then Mathematica says, OK, this is it. But if you want to manipulate a little bit this, you want to make this, let's say, 22. Now you get a bigger one. But in Mathematica, you have something, it's called dynamic. You can manipulate this. And now I could say, let's call this n. And I say, I manipulate this n from 1 to, let's say, 100 in steps of 1. That's all you have to write. And now Mathematica automatically makes a Java applet with a slider, and you can do interactive algebra. And you can put everything in here, every formula, every graphics, and with one slider you can see how sensitive is it or what happens. You can make one slider, 10 sliders, two-dimensional sliders, all in one line. It's so extremely 21st century that I don't understand why people are still working with programs from the 90s. This is all, everything I show is virtually impossible in Python to do all these. And I'll show you more small things. OK, I have my net model. And now I want to look inside this model. What is it doing? So we have this first layer, conf11, and conf12, 21, etc. They all have names. And what I do is I cut the network. I just say, let's take a scissor, and I cut it here, and then run the network and just put the camera at the end. What does it see? And I do this for several steps in the network to see what is this guy doing. And I have to give it some input image. And I've decided, let's give it an input image for my camera. So I first take the layer into the first layer. So now I have a very short network that is doing only the input, layer conf11, and the output. I take another one up to layer conf22, and I call that short HNet. And this is a little bit longer. It has more layers, and it has now an output of this. And I take a much longer one, up to 5.3. And from these networks, I'm going to look what they do, actually. I open my camera, and now my camera is looking at me. I see the light turned on. And now I can do a current image. That means just take the image from the web, do a dynamic, keep going on, and then show these images. So what I do is put current image right here into short HNet22 into short HNet, this one. So I get a whole bunch of these images. And now the network is dynamically processing my image. Let's make it a little bit higher up. And as you see now the different layers. The top row is, yeah, it's not interesting to see me, but I can wave my hand. It's not really real time, but enough real time to see what happens. And you see what the first layer that's on the top row is now actually doing. And it looks a little bit like edges. And this is more complicated. And this is very complicated. How in the world can we understand what this layer is doing? For example, this guy here, this white dot, seems to be my face. Yeah, the resolution is indeed going down. And you see, if I move around, it moves around too. If I go up, it goes up. And look at this particular image, for example. You see that it seems to detect my face. And it's a little bit slow, but it does it. If I put my hand there, it doesn't react. So it's probably very face sensitive. And that's nice. So we have a face neuron here. That is what they found in the brain too. You have neurons that only fire on the face. This is the grandmother cell, or a very nice beginning of it. And you see it with one-line programming or a few lines programming in Mathematica. You can actually visualize this. Yeah, the last row is the deep network. Let me close this now, because otherwise it takes too much computing power. And I close the camera. The last row was showing this long network. So it was looking very deep in the network. Nobody knows. That's the big problem. It shows an image of 14 by 14 pixels. So it is a very low coarse resolution, very deep. Well, this is layer number 40. So this is a very deep layer, what it shows. So this network is, no, actually 53. So this is, I took a short, the first few layers. I took the first, 22 layers, and I took the first 53 layers. And the first row was showing the first layer, and that just does some edge detection. The first 22 layers do something more sophisticated, and then we get deeper. So you see, well, the features sum up to a face, it looks like. And now I go deeper in, can we understand what these features do? I go... Actually, I skipped this. There is a very nice Google Deep Dream algorithm. And Google Deep Dream, it's programmed right here, but it takes 5 minutes to calculate. I want to show much more, so I could show you how... No, actually, why not run the whole notebook and show you in a few minutes what happens? So I say evaluate the whole notebook. So now it does everything. It reads my network, and it extracts from the networks the first layers. And these are the first layers in my network. And they are the filters. And nobody knows, my goodness, what are these filters? It looks a little bit like line detectors in different directions, or edge detectors, that they look at the difference between black and white. And some are blob detectors or color detectors, but very simple, very basic. A little bit like lines and corners and edges. If you blur them a little bit, you see a little bit better that This looks like an edge detector, black-white. And this looks like, this looks a little bit like a line detector. You could also say it's second-order detector. Google Deep Dreams algorithm is famous. And I look again into these layers. And what I do is I give the input to the network not an image, but I give it just plain noise. And if you give it noise, that's actually all kind of information. There is no structure whatsoever. There are no lines, no faces. It is just noise. And this is the visual noise, colored noise. And if I give this to the image, it gives me noise as output. But it turns out, if I shake the noise a little bit and I start looking into what happens, then it has calculated in the deeper layer, hey, it's seeing this. And this is actually quite interesting. This is just a random layer somewhere, and it looks like little birds. So it has found some patterns that there must be a bird detector layer. And if you do this for hundreds of layers, you see then they cover all kinds of things, so that the patterns become more complicated. They're not lines, or not just noses, but they're a little bit more complex things. It's very fascinating. So we now see highly structured stuff. And in the first layers, we see coming up textures. In the next layers, we see this was trained by ImageNet, 1.2 million all kinds of images. The classic images that you get from the internet random. So these were images from animals, beaches, cities, faces, everything. So it is quite random. If you train this network with other data, let's say medical data, you get tumors here, blood vessels, hearts, you name it, ribs. It depends on what you train it. So this is actually quite nice to see what happens in here. Okay, just to show you that it's possible to look inside. Now I go fundamental. And I go look a little bit at why do these first filters come up? And I start in a pixel, a stupid plain pixel. It's the best beginning I can do. Where should I start? So what I could do is show you this guy. It's Abraham Lincoln. And I do now an image resize, so I go make this image less pixels. And I do this manipulate function, and I change n, and n goes from 1 to 200 pixels. And I start with 100 pixels. So this is Lincoln with 100 pixels. You see 100 here. Now I make image Lincoln more pixels, and you actually see no change. But if I make Mr. Lincoln less pixels, and you see exactly what happens here, I get a lower resolution image, and now here we see his pixels. If I go to the last pixel, just 1, that's the average. And here we have just 4 pixels. But there is something very stupid here. Mr. Lincoln has edges and corners in his face. And that's completely artificial, because we made this very stupid square pixel. So why should it be a square? That's ridiculous. It introduces information. So a square pixel is the source of a lot of errors and a lot of things that you don't want to see. A network doesn't want to see squares and corners. It wants to see a smooth face. So let's have a look what is actually the best shape of a pixel. And of course the pixel should be circular, it should be round, because it should not have corners. It should not have steep edges, but it should be a little bit smooth. So it should look like, what we call a Bell function, a Gaussian function. That might be the best filter. But how can you prove that? It was Mr. Dali who was very much charmed by this first picture. It was he made this beautiful painting. This picture of Lincoln was published in a very famous Scientific American paper, so all Americans saw this picture and recognized immediately Lincoln, even if it was just 16 pixels. Okay, if I blur this, and I just say in the manipulate blur, and with manipulate I can just see a little bit, blur it a little bit more. So if I blur this a little bit, you see, now I get much better visibility of, it's still a low resolution, but the edges are gone, and the corners are gone. So how can I derive the optimal pixel? And now I go do a little bit of mathematics. And I know that for some of you will be quite complicated, but I skip the details. But this is what you called first principles. Let's start at the very, very basic thing. And the pixel is an aperture function. Through the pixel, my light comes in. If I have a pixel on the camera, I measure the light with that pixel. And I like to make it as small as possible. I cannot make it really zero, because then there is no light coming in anymore. So it is always finite. Small, but not zero. And the pixel is everywhere the same. So wherever I move my pixel, this pixel is measuring in the same way as there, so I can move my pixel everywhere. And if I increase the number of photons in my pixel, I give it twice as much light, I get twice a high number. So it is a linear system. This all means it is a convolution. And this means I have my light outside, and this is my filter. X minus alpha means I shift it. And I multiply my image with the filter, and that is how I measure. And I integrate. This is integration, that means add them all up. Okay, so now I know this is a convolution. But I know a couple of things from this convolution. If I take my, G is my pixel, and I have to find what is the formula for G. And that's a little bit complicated, but I know that if I have a pixel, it is not multiplying something, it is not decreasing, it just takes the full value. If I take the whole pixel, everything of it, it multiplies by 1. So the integral of this pixel is 1. The mean of the pixel can be any value. I give it 0 just for convenience. And the size of the pixel, I don't know, but I give it sigma. Now I want to have something in physics. I don't want to have junk. And what is the physics for chaos, random stuff, all kind of junk, is called entropy. And entropy, you may have heard of it from physics in your high school. Entropy is something for, it's a physical measure for chaos, rubbish. And I want to be the things as smooth as possible, so as little as possible chaos. So I take the entropy, and now I go and find the maximum entropy, that is the maximum smoothness. But with the 3 constraints that I say, I have this one, and this is 0, and this is sigma. So I have now to do an optimization, that's how it's called in mathematics, given these 3 first principles. And this is what's called Euler-Lagrange. And Freddie knows very well what it does. I worked my whole life with this kind of optimization, and it's a very nice technique. So I make the entropy, and I say, okay, just add the other ones. I didn't know how much, so I put some constants, lambda 1, lambda 2, lambda 3, and I do it now in Mathematica. And yeah, you get a nice formula. But I want to have the optimum, and if I have the optimum of a function, how do I know where I'm on the optimum? Well, if I have a function and I put the line that is just touching, if I'm on the top, it's a horizontal line. And here it's not horizontal, there it's not horizontal, but I want it to be horizontal. And if it's horizontal, that means there is, it's called a derivative, that's 0. That means it is really not changing at all, it is just horizontal. So I want the derivative to be 0. Okay, and this is not a derivative to x, but to a function, so I need a little bit of variational. And now I go solve it. I just say solve it, for this, var is now this, you see it is now some function. Solve it for being 0. Oops. G is something interesting. G is some exponential function. Let's make it a little bit bigger. But I have still a problem. I still don't know what is lambda 1, what is lambda 2, and what is lambda 3. Help, how can I do this? I need to get a little bit of a trick. And the trick is from algebra. If you have 2 equations with 2 unknowns, you can solve it. If you have 10 equations with 10 unknowns, you can solve it. You need a computer, but you can solve it. Now we have 3 unknowns. So what we need is 3 equations. Well, we have the 3 equations because these equations are, this guy is 1, this guy is 0, and this guy is sigma. So let's just plug them in. And we ask in Mathematica, this exponential function, put it in here, and calculate this integral, because I put it in the first equation, tell it that it is 1, and simplify the equation. And now we get the force of Mathematica. It can do real mathematics. So it is now putting this exponential function in there, chunk, 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 and calculating, my goodness, something very complicated. I do this for x times this exponential function, and put it to 0, let Mathematica crunch, and now I get equation 2. And all this is real time. And you see it is very nice. Lambda 2 is 2, and now let's calculate the third equation. And that means I have 3 equations with the 3 lambdas, all terribly complicated. But I really don't care, because Mathematica is doing all the mathematics for me. So just what you say is to Mathematica, solve it. And what do you need to solve? A set, and that's between these curled brackets, of these 3 equations for the 3 unknowns, lambda 1, lambda 2, and lambda 3. And in the end, simplify the whole thing. Oops, it finds something. Lambda 1 is this, lambda 2 is 0, lambda 3 is that. All only have to do is to put the lambdas into this exponential form. So I say slash point, that means replace. And there we go. Hey, this function for physicists is very famous. This is the Gaussian function. This is exactly the function that I expected, more or less. But now I know it is the unique solution. It's the only solution. There are no other functions. This is the one. This is the best pixel. So we should forget about square pixels and only use this one. If you plot it, of course, you get all kinds of nice functions. This is now the famous guy. This has no steep edges. This is, if you put this in 2 dimensions, you get this famous, here you get this famous plot, and you can turn it in all kinds of shapes. So now we have found the best pixel. Let's go a little deeper. If you want this, I will do a little bit fast. If I now go study the little bit the neighborhood of my pixel. So now I started in the pixel to understand deep learning, but that's not enough. I need to go further because I want to go my context, you remember? I want to go what is next to my pixel. So make it a little bit bigger. So let's now take the surrounding of this pixel. Because we want to understand perceptual grouping or visual binding or contextual processing. How does it really work? And if I take, for example, a hand ray image, an X-ray, you see the bones, I can make this image into a 3-dimensional image. And now intensity is height. So I get the landscape, and you see this is now my hand in 3D, and where it is white, it's higher. And you see I have height lines, and I can find a little bit what is the local shape, what is the curvature, is it very steep, is it flat, Is it curved? Is it shallow? Is it hollow? Is it a ridge? Is it a valley? So I like to do a little bit of geometrical things. And if I go, and this is too complicated, I guess, for now, but I just want to tell what happens. If I go from fx to fx plus a, I need to have a mathematical operator that does that. And it turns out, and I explain it very nicely here, to be the exponential operator. And the exponential operator is nothing else than the Taylor expansion. So if I want to find the description of a local point a little bit further away, there's a famous mathematical technique, and that says, if you know the local shape, you know what is the pixel next door. If you know that you're on a slope, well, the pixel next door is given that slope further down. And there's a beautiful explainer on the internet, and that's called 3 blue, 1 brown. And this guy, not sure if it works. Sound is not working this time. Oh yeah. He gives...
When I first learned about Taylor series, I definitely didn't appreciate just how important they are. But time and time again, they come up in math and physics and many fields of engineering because they're one of the most powerful tools that math has to offer for approximating functions. I think one of the first times this clicked for me as a student was not in a calculus class, but a physics class. We were studying...
I'm not going to show this, but this guy is world famous for how nicely explains difficult things. And I'm going to use a little bit of his techniques to show how this actually works. If you see in Mathematica how this works, in Wikipedia, you see you have a function here and lots of these functions, and you see a complicated graph. If you do this in Mathematica within one line, you have exactly the same function. And it automatically changes. But with manipulate, you can make it even easier. And you say, okay, let's move this point and see exactly how well can I describe what is next door. And you can make higher order derivatives. Okay, this is more for the mathematical people. I want to go a little bit, skip this and go to the next phase and learn the first filters. So let's do we remember this image. And here we see the network. And I'm interested now in what happens here in this first layer. And then I go to the second layer and say, can we really understand why these guys come up? So I go do like a monkey, millions of years ago. And I'm the first brain that is being trained. So let's have a look. I skip all this. I go look at what the monkey is seeing. And I expect the monkey to see a forest. I could not ask him to see a church or whatever, a building. He's seeing nature. So let's take a nature image, and this is a random image of a forest. And now let's make some small patches of forest. So I divide this image into very small 12 by 12 pixels. So very small squares, lots of them. And I show here a few. But if I have a look at how these images look like, I have 49 by 49 images, each 12 by 12. So this is what I see. But of course, I have a Gaussian pixel. So now, this is actually what I see. So everyone has now, with the edges removed, it is now a nice pixel. And now I go do a mathematical trick. It's called PCA, Principal Component Analysis. And I know that's a little bit difficult to explain exactly what it is. But if I do principal component analysis, I have to take every little patch here, and I put it in 12 by 12. I put it in a long column factor, 144 numbers. And all these columns I put together, and then I have a big matrix. So I get a matrix of 144 by 2401. Can I see this matrix? Yes. Not so interesting. But every horizontal line is now a stretched out small patch. And I want to make it square. Well, there's a trick to make it square. You take that matrix, you multiply it with the matrix 90 degrees rotated, and you get a square matrix. And from this matrix, we can actually have a look at this matrix, not so interesting. We can calculate the eigenpatches, the eigenvectors. And these are the eigenvectors. Hey, these are the eigenpatches. And this is the most simple representation from all these patches. Because what I can do now is I can say every little patch, no matter how complicated, I can make as a sum of these simple ones. So if I have 16 simple ones, and I just make a simple combination, half of it of that with 1/3 of that, with 0.2 with that, I can make any other one. So this is the most basic way of representing any patch. I don't need to learn all of them. All I need is to have this basic set, and then the weights in my network can make any one. So the fact that I have now a very small representation, that's ideal, and that's exactly what the brain does. So the brain is not learning all these leaves and all these images, but it's just saying, give me millions of these small patches, and I extract what is the basic set. And that's very, very insightful, because now we have this set, and we can also see that it is the Gaussian. And this is the first derivative of the Gaussian in the vertical direction. And this is the second derivative of the derivative in the... So we get all these derivatives, and that's actually what the brain is doing. It is not having features or line detectors. It is taking derivatives, and you see it right here. It's doing geometry. And Freddie knows all about the differential geometry. This is a Taylor expansion around each point. It may seem now very simple, but nobody has written this down yet, that it is so simple. We need derivatives, not Gabor functions. Gabor functions are completely not adequate, not funded. They're completely out. Everybody talks about Gabor functions because they look like this, but they're very different. And you can look at eigenvalues, etc. And now let's have a look at what we see in the network. And this is actually what we see in all these trained networks. And see how nice it is. They very much look like the filters I have here. So this guy, white to the left, black to the right, you see it right here. So this is exactly what these filters learn. And if you look at the visual system, this is a Nature publication where they measured with a needle in one of these cells, and they gave it some input to I think it was done in a cat, and they measured then the cells in the cat. What happens? And you see, hey, it is white, dark, white. And that's exactly this one. So the brain, the neural networks, the mathematics, they all do the same. And we now understand a little bit better. This first layer is now very well understood. It takes plane derivatives to measure geometry. And when it measures geometry, it can find all kinds of ridges and edges and contours and texture. So now we understand this much better. And the next phase is, of course, how do we combine those? That will be the next chapter in my book. I don't have enough time to explain today because I have only 3 hours, but that's a very exciting step. Then we can do perceptual grouping. We combine, in a short term, it's tensor PCA. So instead of single values to find the most concise representation, you have now a whole stack of derivatives and you find the most representative. Let's have a look a little bit when I take a special image. So if I take an image of a forest, and in this image I have only vertical lines. So now I have not, and now I did exactly the same. So the code above is making this principal component analysis, and now I get different filters. So this was an animal that lives in, only horizontal stripes. If I go vertical, there's nothing changing. So there are no derivatives in the y direction. There's only derivatives in the x direction. And that's exactly what you find. You find the first derivative in the x direction, the second derivative, the third, and only here you find the first derivative. So it matters what you feed in the system. If you give a child that's just born, it can only see horizontal trees. It never makes these vertical derivative filters because they are not there. You don't have to learn them. And that was actually done in a famous experiment with the cat. And I have a small movie here.
We regulate the visual environment by keeping kittens in complete darkness from birth, bringing them out for periods of controlled visual experience inside special cylindrical chambers. Here, a kitten is being exposed to an environment consisting entirely of horizontal stripes, and it wears a ruff to prevent it seeing its own body. This particular kitten will be exposed to these stripes each day from the age of 3 weeks until it is 3 months old. All the rest of the time, it remains in complete darkness.
So it's a pretty heavy experiment, but they put this kitten from birth, it had never seen anything else, in only horizontal lines. And now the trick is, what does this kitten learn?
But its vision is not really complete. Watch the way that it responds to a shaking horizontal stick. The kitten can see it. But if the stick is made vertical, the kitten no longer reacts to it. Remember that this kitten saw only horizontal stripes when it was young.
So this kitten is severely limited. It has never developed filters to see vertical things. So that's actually a lesson. If you have a newborn child, give it a wide variety of impressions, then it will build a nice visual system. If you restrict it, it only sees a white ceiling in the first 3 months of your life, it will be less learning. So that's what most parents do. They give it lots of colorful blocks and toys and so on, and that's exactly what you should do in movement. So this is 1970, long time ago. That was, the movie was a little bit slow because we have a much faster lifestyle, so we think we already expected what was coming, but in those days it was. But you see now the nice relation between a biological system and a deep learning system. The training is more or less the same. In deep learning, we change our connections, the weights between the network. In vision, we change our synapses. They just blow up. You can see that. And they shrink. Okay, yes. I think so. There was a little bit the problem with this that it was not longer considered ethical to do this kind of experiments with experimental animals. So it was a little bit limited. So you cannot do infinite experiments with so much time and so much time. But what was, of course, these experiments were done tens of times, but not all over the world, lots of times. It was a little bit limited. But what was found that for humans, you have a critical period of about 3 months. In the first 3 months, you learn all your neural network. If you don't use those 3 months, your network is more or less fixed. And so the first 3 months are quite critical. That's the formation of all these. In the beginning, your neural network is abundantly wired. Every neuron is almost connected to every other neuron. It's ridiculous. There are far too many connections. And if you develop, if you learn, you start seeing and moving, you take out these connections that you don't use. And that's actually what happens. And that happens in the first 3 months. Of course, you keep learning the whole rest of your life, but the basic, let's say, structure, the basic platform is formed in those early days. Okay, let's take another next step. I have a little bit of a this is how you build a self-driving car. And now we're gonna use a little bit this network. And what I do is in Mathematica, I just make a kind of a road. And I have this road right here. And on this road, I put a small car. And this car, oh, sorry, I made a mistake. Actually, I'm too early to show this. How much time do I have left? Till 1 o'clock, about 10 minutes? That's fine. Okay, I will stop about 1 o'clock and then ask some more questions. Because I can talk forever, as you see. I have a lot more to tell and have a little bit to pick out a little bit. Yeah, 1 o'clock is fine. If we talk about all these features in network technology, everybody is talking about, it should be invariant. And invariant means that whatever I detect, it should not depend on where it is, or if it is rotated, or if it is smaller or bigger. How can I actually do that? And if you look at invariance, you can use Wolfram Alpha. You all have heard of Wolfram Alpha. It's the Wikipedia on the internet. You can ask any question. It's quite sophisticated. It was written by the same guy who wrote Mathematica. And Wolfram Alpha is, of course, very much part of Mathematica. Actually, Wolfram Alpha was written in Mathematica. So if I ask what is invariance, the quality of being resistant to variation. Okay, how do I vary? Well, it turns out that in mathematics, you need a matrix and to multiply with the matrix. Well, in Mathematica, that can be done very easily. This is the matrix. And I have this matrix to do the translation and the zooming. And I have another matrix here, and this is the matrix, you see cosine and sine. This is doing rotations. So I have a translation and a rotation matrix. And now in Mathematica, it's so nice, you can do a manipulate. So if I manipulate the A, and here you see I can manipulate the A from 1 to a zoom factor. I start in point 2, from 1 to 2. I can also manipulate the B and the C and the D. I can manipulate the phi. I can manipulate the X and the Y and the S. And you see all these are in an extremely simple formula. And I do it on this image. This is my cat at home, sitting on a nice rhino. And I multiply this image with the two matrices. So let's see what happens. You see what an elegant way of programming this is. It's directly the matrix. It's not just a small line or so. You see, I have a real phi here. How do you write a phi? You just say in Mathematica, escape F, escape. You get the phi. Escape A, escape. Escape pi, escape. Escape inf. And this is how you make all these nice characters. Escape capital pi, you get a capital pi. So I have now really phi, etc. But now let's have a look what these transformations do. And of course you expect what it does, but in one line of programming, I have this beautiful thing. So if I have the translation, it does it. And you see how fast Mathematica is. And the translation in Y is just this direction. So now you immediately see what happens. If I reset, it goes back here. If I rotate my image, very easily, but of course you see it rotates around 0. This is the origin. If I zoom my image, you get the zoom. And it's nothing else than changing the parameters in this directly visible. You immediately recognize it because this is how you write it in the textbook. If you see this in Python, this same code, it's completely unreadable. You will never convey this to a non-expert in Python. But this is easily understood for even first-year students. And you can, of course, do the shear. So we have all kinds of transformations we can nicely do, and we have it interactively, mirror, you name it. Okay, I can now make all kinds of features, and let's take an image. And this is an image in pixels. It looks like letters, but these are just pixels. And if I have now a corner filter that finds where are corners, you get them right here. So it has now detected corners. And now I go rotate my image. So I say image rotate, the image of the letters Fox, over phi. And phi is my angle. You see, non-programmers, how easy it is to program. Just say image rotate this image over phi. And then show it framed and compose the image with the corner filter. So here I have it. And now you can rotate it. And you see that the corners do a just as good detection no matter how it is rotated. So this detector is a really nice invariant detector. You see the proof right here. And now everybody is working with all kinds of this geometric transformations. You will hear later of this. Michael Bronstein is very famous working on these all kinds of transformations, and yeah, he will tell more about it. If you look at a neural network, you will see that we are actually not rotation invariant. We have never seen text upside down, so it's pretty non-trivial to recognize what is written here. You cannot immediately see this. You can immediately see this one. And if you see, for example, Margaret Thatcher, it's a famous illusion that the lady is already a long time ago, she was Prime Minister of the United States. This is a rotated version of her, if I change the rotation to more normal, you see the difference between the two. This is a ridiculous image in which they have just taken out the eyes and rotated it, but you couldn't see that in this image. Now you see it a little bit because you know, but in the first time you didn't see it, because we never recognize images, we talked about it before, upside down. So what you see is what you learn. And that's exactly for neural networks. That's a little bit the lesson of what I like to give here. Let's take a neural network that takes particular points on the face. So I load the network. I take a familiar face. I could take any face, but not to harm someone. I take my own face, can do whatever I like. And if I ask to measure in this face particular highlight points, it does that. It makes 68 particular points. I go skip how you calculate it. It measured heat maps. We're going to measure on these heat maps how they do. Let's all forget about it and calculate the thing. This is what the network does. And it's quite cute. It gives me 68 points and it groups them, and it finds in my face key points, important points on the face. And these are used to recognize a face. If I open my computer, this is a very modern computer, the only way to open it is to put my face in front of the camera. There's no other way to open my computer. It recognizes my face. So it is a very modern biometric lock, as you call it. Okay, now I have this, but now I go do this function, and the network was netmake model, with a manipulate. And with manipulate, I manipulate phi from 0 to 2 pi. And I put this manipulate in an image rotate. So I do image rotate, my face, over phi. So I just go, and now let's see what it does. And each time it calculates the points in my image. There we go. I rotate my image, and you see it does a really good job until I'm here. This network has never seen faces upside down, so it doesn't know what to do. So networks in general are not rotation invariant, despite the fact that everybody wants them to be so, but we as humans, these types of networks are not. And there's a big rotation difference. You can have rotation in a point, or you have rotation of a whole context. And I'm now talking about rotation of a whole face, of a whole context. And you see that it is quite important to realize what happens. And the nice thing is that you see how short this is programming. I made all these decades in my career immense speedy progress because I never had to program long lists of programs. I could everything do it in a one-liner. If there was a paper coming out on rotation invariance, you program this in more or less 5 minutes, and you can immediately see what happens. And that's the value of high-level programming, that you can do so much faster. If the program takes 2 seconds or 4 seconds, I don't care. But if the designing of the program takes me, let's say, half an hour instead of 2 days, that's the biggest time change. So now you see what happens. And if I rotate further, and you see it's fast enough. It's not really real time, but within a second, I have a rotation of the image. And this includes a lot of calculations because the whole network is now being used. Okay, I have a lot more to tell about what happens in the image, etc., and about shapes. I leave it for the people who want to dive further into this. As I told you, on the website, there is a lot more coming. How to design a self-driving car, how you use with these filters, lots and lots of it. And when my book comes out, it's actually not a book, as you see. This doesn't fit on paper. You have to read this book interactively. And it's now a time for social media. So my book will appear as 7-minute YouTube movies. It will be published in medium.com. But then lots of them. Nobody will sit down for hours, but you have very short things. But I make tens of these movies. I'm already doing it. I have a nice studio at home, and I talk like I do now, and then I give much more explanation in detail about what is the code doing. And this book is then a very modern, let's say, interactive tutorial book in which people can have directly their own code. So you need Mathematica and do directly what I do as well. But then the learning process turns out goes much faster if you do it than when you just read about it. And that doing is what I think Mathematica can do in its ultimate. It's called a computational essay. You have a story, and this notebook that you download has also, I didn't show it, but it has a notebook, and that's called Learning Mathematica in 5 minutes. And that's actually, I didn't learn your Mathematica this morning. You just saw it, but you more or less understood image rotate. Yeah, it does an image rotation, and it's so logical, you'll learn it really in a few minutes. And here I give a little bit more how you make a pi and how do you make a square root, etc. So a little bit more details, but it is so high level, it's so English, you can speak to it that it does it.